says diamonds and gold will be very tiny, but they worth a lot. So I believe that would be worthwhile visiting this conference and participating and presenting, even though that's compact. Because as Chair explained, there are certain reasons why so many people could not make it because of the visa issues. Anyway, let's get started. We are a little bit behind the time schedule. The first presenter, it looks like my name, but actually I'm not. I was going to enjoy with this conference just being, observing who's presenting what, the ideas to pick up and question, understand some of the things, learn, and also to see my grad students. Half of my lab is here. The first presenter is going to be Mr. Brady. I have difficulty to pronounce his last name. He's my PhD student, Lindsay, and also his co-speaker will be Jewel Woodcock, and she is my undergraduate research assistant. They will present the paper is called Vibrational Response Measurement and Analysis of Honeybees Using Laser Vibrometer and High-Speed Camera. Floor is yours. Ready? Please. Thank you. If you want to add a couple more comments about yourself, please welcome, particularly your background with the honeybees.
Okay. So, hello everyone. I am Brady Lindsay. My background with the honeybees is yes, sir. My background with the honeybees is part of my grandfather's. So he has been a beekeeper for around 20 years. So that's kind of where our passion for this research comes from as well. As Dr. Sulman mentioned, this is going to be the vibrational response measurement and analysis of honeybees using a laser vibrometer and high-speed camera. For the importance of honeybees, there are many reasons. 75% of the crops and around 85% of the flowering plants do require pollination. So honeybees are vital to natural and agricultural environments. They're also one of the few manageable pollinators other than bumblebees and the alfalfa leafcutter bees. So honeybees generate over 250 million in pollination services, and so that means, like in California, they transport 2 million hives to help pollinate the almond trees. So that shows that there's already not enough natural pollinators around, and so we really need to help keep the ones that we do have the ability to manage. And as you can see this year is highlighted, but last year's loss was actually over 60% of all the colonies in the United States. So that is a big chunk out of the whole economic side of that. So one of the challenges with the monitoring of honeybees is it's stress inducing for the hive and the bees themselves. It's also labor intensive and it's prone to error, just human error, or you might accidentally kill the queen bee or something when you're inspecting the hive, and things like that. So a challenge is to try and monitor these responses and these stressful conditions before they become a problem. So another challenge is also to extract these individual communication signals from the bees and then to validate that signal as well, instead of just assuming that it's a vibrational bee signal but you don't really know what it is. So our research objective is to measure these vibrational responses without contact, and we do that by using the laser vibrometer, and then we'll validate these signals that we capture with the high-speed camera. So this is our experimental setup. So there's a lot going on, but the main things is the laser vibrometer, and that will collect our vibrational signals. And that's focused at the target here, which is the frame display that we built. So what we'll do is take a frame out of the hive and put it in this, and then that's where our laser is focused on here. And so that's collecting our vibrational data, and then we use the high-speed camera to kind of validate that as well, so we can see, you know, what the vibration or what the laser barometer is looking at, as well as what the bee is doing at the same time. And so all the vibrational data is collected on the IMC DAC, and then the camera is collected on the camera's SD card, and then everything is run. Oh, sorry. Everything is pretty much operated with this laptop, and the other part of this system is the shaker table. So with this, we can set this display on here with the bees, and then the shaker table, we can tell it certain frequency or certain tests that we want to perform, like a random vibration test or sign sweep test or just a sign dwell test. So we can tell which frequencies we want the shaker to shake at what magnitudes, and then we'll try and read that response after the excitation has stopped, and we'll try and read that response and compare a calm reading to an after excitation reading and see if there's a difference. So to help kind of explain that a little bit more, this is how we take it out or put it into display. So we'll look for a frame, and then if we choose one, we decide, then we put it in the display, and then the display gets put into the onto the shaker system. So then this is kind of our point of view. So like we're looking through the camera at not only the bees and the laser focus, but also you can see the monitor in the background is showing us the timestamp, and this is one of the slides with the video. I don't know if it'll play. It's just like, I think if you hover like right around here. Sorry. So this is kind of just a video to help kind of show that, and it doesn't have to be zoomed in, but so you can kind of see the laser right there focused on the bee, and then we capture the timestamp in the background, and that's how we synchronize our, you know, the vibrational data to what we're seeing on the bees. Otherwise, we would have a lot of vibrational data, but couldn't really say for sure that that's what the signal was. So once we collect that data, this is kind of our flow chart. So we have the different samples coming, or the vibrational data coming into the DAC, and then the videos on the SD card. So once we organize those, the videos actually get organized a little bit further, and they get organized by their body regions where the laser was focused. And then once that's all organized, we'll put that together in a data analysis folder, and that's where we can store it or share it with other users. And then that's where we usually start doing MATLAB analysis. And as you can see, Jewel is right here. She's reviewing the videos, so then she's going to look for the timestamp, and then also where the laser was focused on the bee. And then once we have all that organized, then we can start getting some plots. So we'll look at the time domain data first, and then we'll use those timestamps that she decided, and then we can trim the vibrational data to where we just have specific samples focused on which part of the bee and what sample they were from, which test they were from. And then from there, this is what we'll get. So we'll have our time domain data, and this is a 1 second trim second. And then from there, we can do a FFT analysis of this time domain data, and that will show us the frequency, predominant frequency that was captured during this segment. So for this one, this was under a calm condition for any excitation. So you can see that the frequency capture here was around 9 hertz, and then after excitation, same thing, it's just the frequency is a lot lower. So we kind of thought the opposite was going to be the case, kind of shaking the bees around, we'd get them more agitated, but we actually saw that after excitation, the bees are kind of like almost trying to get back to normal, I would say. Like they're really slow moving, if at all, and then they're also trying to like clean themselves, it seemed like, if they got dirty from like honey or pollen being shaken on them. So what this means is this methodology could help identify and verify the individual vibration signals, and especially without contact. It also increases applications for the vibrational measurements by synchronizing the high-speed camera with that. So from these studies, the vibrational sensors do provide a better way of assessing honeybee health as it's a means of intentional communication. And so this really helps say specifically what that signal was that we captured. But there are limitations to this. It's very difficult to acquire these samples because you can have everything kind of set up and the laser focused, and then you hit start on the camera and then the bee moves out of the way. So then you have to redo everything. So it's also limited and lack of samples to compare to. It's all kind of new, so we don't really have old data to go against, but then also it's like looking at our new samples, it's just hard to collect a bunch of samples, so it's, yeah. And then it's also an unnatural environment, so we're taking them out of the hive and then putting them in this display, so it's not technically in a hive that's producing. It's and then there's also other external vibrations that we take into account too, like we have an exhaust fan that's part of the system that's required. Other things like this that we have taken into account too. But for the conclusion, our research objective was to measure the vibrational responses without contact, and then synchronize and validate those signals with the high-speed camera. And so the key findings for this study was the high-speed camera synchronization really helped validate and increase application for the vibrational response measurements. And then also the laser vibrometer provides a great way of measuring these signals without contact, as opposed to like trying to put an accelerometer inside the hive or something. So for our future research, we've changed a lot since then. I mean, we moved the whole system to the other side, and then also we've added our new high-speed camera. You can see kind of right here. So this is a Phantom Hero high-speed camera, which has been a great help to us because it's now, like before the camera was a separate system, so we had to just try and combine those data sets. But now it's actually all connected, so it actually works really well. So we can just basically be looking at our camera screen or the camera software, and then whenever we see a bee come into the focus, we can hit that capture, and that will tell the DAC to start recording all the vibrational sensors and everything. So everything's hardware synchronized. And then here is a video from the new camera software. So instead of trying to look at the bee and the laser focus and the timestamp as well, now we just have this high resolution slow motion image that we can, a lot of AI applications could probably be used from it as well. But yeah, so this is similar to the software. So really, we're just looking at this screen now, and we can hit, there's a button down here that says capture. And as soon as we hit capture, it starts all the vibrational recording. So everything's just kind of put together. And so since then, we've collected a lot more samples and a lot more tests. So this is just one sub-test of one frequency, and this is only one body segment. So there's a lot more samples than this, and we really just kind of got everything working really well, and we're able to collect like a lot of samples now. So we have not really went back through these and kind of, seeing which ones are the best samples and kind of eliminate those. But this is kind of just showing like we're able to get a bunch more samples, and we're working at going back to look at those. But the first two up here are, this is the calm and excited again, and then this is where we can see them combined. And then hopefully we'll see a difference versus calm, normal conditions versus excited conditions. And then we can kind of see which frequencies and magnitudes affect them the most. So for a continuation of that, obviously we have 2 hives, I think, full data sets now. So we're trying to get the rest of or more hives. Also some winter testing, as it could be a little different. And then the larvae and pupal cycles, we have one larvae set already. We're working on collecting another. Bees of different age groups and castes, and then also the full hive with a queen to simulate the most natural environment there. And then also the AI-based analysis and identification patterns. And then I know we talked about taking measurements of hive inspections and during transportation as well, and then play that back through the shader. Our funding was provided by the USDA grant, and then we want to thank everybody at the USDA and NDSU, and of course everyone here for your time. Thank you very much.
Great. Please, any questions?
Thank you for your very detailed and interesting research. It was very interesting. I have a question. When you use that laser vibration sensor, after that you check it with high-speed cameras. And how you check it? Do you have like standards or more standards for bees vibration or something?
You mean to compare the signal that we have compared to what we had before? I would say no, because I would say the validation was more of just seeing that the laser was focused on a bee at the time instead of maybe just the bees were all around, but the laser wasn't really, it was capturing data but wasn't really focused on a bee. The validation I'm trying to say is that we can say that the laser actually was focused on this bee, and if the bee was moving or if the wings were flapping or the abdomen was moving, like we can say for sure that signal captured by the laser was for that bee doing that movement or that. I don't think we don't really have anything to compare that to, because I know I have not seen any like that. So I guess the signal that we captured to validate that, I would say no, but I think it's more of the validation of saying that vibrational sensor was actually capturing that movement or that bee's movement instead. Is that kind of what you're asking? I'm sorry.
Yes. Okay. Thank you.
Sorry. Thank you.
Yeah. Thank you.
Please.
Yes.
Thank you for your presentation. I have 2 questions. First is there any simulation platform, simulation frameworks for that without using like experimental setup? Just let's say I want to work in that, can I use just a server, some simulation? This is the first. And second question, I'll remember and answer.
So for using the simulation software, I am not very familiar with the simulation side of it, and I know this is very new data, so we still need to process that. I know that what I used to make these plots was MATLAB, and I know you would be a better person that would know the MATLAB simulations, but.
And second question, about the real world implementation and scaling of the system. Let's say I'm the businessman and I want to use your solution. How I can use your solution in my, let's say, business.
And you
Scaling and real implementation.
That's perfect question.
Yeah, I would
He
say,
might answer.
yeah, I would say the scaling for this, you're probably not gonna use this system in your business for beekeeping. I think this is more of just the research side, trying to establish a database really of just information. Cause I mean, this is what, $30,000 laser vibrometer and, you know, $70,000 shaker system, and yeah, I don't think it's scalable, but I think it's trying to get it's using the most precise sensor to try and, what am I trying to say? Try and collect really good results to where somebody can use that in a system that is scalable. Maybe that's what I'm trying to say.
What will be like real world application and solution? What will be your contribution in, like, let's say, in humanity, how they will use the solutions, all of this? Let's say in Kazakhstan, I want to use some solutions, I don't know, some data sets, real world application.
So, I know for using this in the real world, I know the one goal that we're looking into is the transportation. So, trying to see which frequencies are affecting them or making them angry or stressed, and then like trying to eliminate those during transportation or something like that. Or if there was like, I don't really know if there was a signal that you captured that you'd have to know if they were unhealthy or uncalm or stressed, I mean, but then you could say, like, if your scalable system was picking up the same vibration or something, then you would know, like, your hive may be infected with a varroa mite, or maybe the weather is making them more stressed or something. So then you could hopefully use this data set with your scalable solution and then be able to monitor your bees without having to use like all this like, expensive equipment. You could do that.
And part of this answer is definitely in the afternoon's presentation that I'm gonna make with their help. So you guys will listen why we are doing this. Of course, it's just the tip of the iceberg he's mentioning, but whole answer will come in the afternoon. Small advertisement, okay? Not the answer.
Thank
Any other questions?
I have a quick question.
Yeah.
Is there any pattern between the frequency and the behavior of the bees?
I would say not yet. I think it's still very early because we, like this last data sets that we have here, I mean, these are like last week, or yeah, last week basically, or the week before maybe. So yeah, like we have not had any time to really look at a pattern, I would say yet. But I think that is the goal, is to be able to take all this data and then apply AI applications for. But yeah, right now, not as yet. It's been tricky to get all these samples because, like I said, it is difficult to capture these bees, like moving out of the way, and it's tricky.
Any other questions? Jewel, you wanna add something?
Yeah.
No, yeah, just.
Yeah, couldn't do any of this without her. So.
Yeah, maybe since I'm not very much into sensors, if it is different, like could you collect some more data modalities, like you're collecting vibration data, but maybe there could be other modalities like sound, if it is different than vibration. Maybe bees transmit something, I don't know, I'm just making it up.
Yeah.
But is there an opportunity to collect different modalities of data instead of single vibration data?
Yes, and that actually is the DAC system. That's actually, I think, what was originally planned was to include a microphone, but then the DAC system actually happened to work with the camera and the laser, so we were able to use, well, yeah. So we can, this DAC system, I think it's 6 channels, and we're only using 2 right now with the laser and the camera to trigger the DAC. But yeah, we could include a microphone and then synchronize this just by really plugging it in, and then we would have that data as well.
Even maybe thermometer, like
Sorry.
thermometer, even maybe just to look at the heats, how heat evolves, and
Heat signature of,
yeah.
yeah, that,
I mean, I was thinking, if you have more modalities of data with
Yeah.
this B environment, maybe it could be
yeah,
More
just more
information.
information.
more
to-
information. There.
Yeah. Definitely. Yeah, I know the DAC system, like we can add more channels to that for the heat camera. That I'm not very sure. I would have to really look into that one. But yes,
Any other questions? 1, 2, 3. Thank you so much, please.
I
you
can have a
yeah,
suggestion.
Yeah.
Because these are very, very important. Because the humanity there, because Albert Einstein has, maybe you know already that, he said one time, if the bees die, in a very short time, the humanity will die. So that's very important because of the agricultural purposes. Maybe young generation would know or not, I'm not sure, but as I was also a hazelnut farmer in the past, I know that your studies are very crucial to understand the social, among the bees, behavior, attitudes. That's very important to understand because some movement of these creatures are not known already, and many different works going on that. Maybe that can be a very good study if you can make parameterization on, let's say, temperatures, humidity, maybe other parameters to understand the behavior of the bees. So that can be a very good contribution to the literature because we know that bees have a very good sensation on the climatic conditions. Even the vegetables and also fluids surrounding them also affects their behavior. And there is no complete study on that, but some clues going on. And on that way, if you can direct your study, that you can have very valuable outcome. Thank you.
Thank you. Yes, please join me.
So maybe you can also.
Yes.
Oh, I can hand over?
The certificates,
Yep.
yes.
Yes, absolutely. First for Brady.
Thank you.
And Jewel, please join. These guys are working hard, days and nights. They don't know the weekends.
I can imagine.
Yes, they don't know the weekends because
You know,
this is the only time.
Dealing with animals are really hard.
Yes. They are very passionate.
Yes.
Thank you. The next speaker's topic is N degree of freedom. I believe it's N degree of freedom, right? N degree of freedom teleoperational system for 4 degree of freedom industrial SCADA robotic control using modular CAN-bus-based architecture. And here we have a few presenters. I don't know who's present here. Sardar Ali or Ahmed Mukhtar or Muhammad Moise, right? University of Calgary. Anybody?
They are not here.
Oh, they're not
They are
here.
not
Oh.
here, right? Okay.
Oh, I have
Maybe
a
we
difficult
can
time
speak
to
to
read.
I'm shining.
I have forgotten my eyeglass, right one. Sorry for that. Yeah, I should print it out, a little big one.
Maybe we can ID 96 maybe.
Yeah, this is tiny ML Reinforcement learning approach for energy efficient light control in locust greenhouse system. And again, that's you, Muhammad, right? Okay. And these two guys. Muhammad, I'm gonna keep track of time, okay?
Which one?
That's it? That.
Good morning or good afternoon, I think. So, again, we are going to present one more work from our lab. It's based on reinforcement learning. It's not no yellow anymore. So that work is technically a tiny machine learning model, and we will know what's the meaning of tiny machine learning in general right now. But the point is here, like we are talking about reinforcement learning, not supervised machine learning like YOLO, the previous one. So the main purpose of that work is just analyzing the performance of using very small and limited computational resources like edge computers or microcontrollers like ESP32 or Arduino board or AVR ATmega 32. In order to do like energy efficient control for any greenhouse system like lighting system or any other systems in greenhouse. So first of all, what's the greenhouse? So greenhouse, as we all know, like it's a greenhouse system for growing plants inside a controlled environment. We actually use a lot of different control systems in order to control the humidity and the temperature and the lighting and every different systems in the greenhouse. And as we all know, like in order to keep all of these things controlled, like the HVAC system or any other systems, we have to use microcontroller or any kind of edge computer in order to do this kind of control. So the need is like we need to know a low cost and efficient real-time solution to do this kind of control, and also accurate and robust with the variations in the greenhouse. So you know, like greenhouse, like especially since it has HVAC systems, that means it consumes a significant amount of power, and it's very important to keep that power as low as possible. And also like the conventional approaches, like just rely on rule-based approaches like if condition. If the threshold of the light is like this, so just turn on turn off the supplemental lighting. The same for the HVAC system in general. So the main idea here is instead of using rule-based approach like if condition or any other rule-based approaches, we need to use reinforcement learning model and deploy that model. And here's the trick on a microcontroller. So we have utilized the ESP32 to deploy reinforcement learning model and to train on the go in real time while the greenhouse is working. So before going to the methodology, actually, what is reinforcement learning model? Unlike the supervised models, we don't need any data to train such model. So simply reinforcement learning model is an architecture or machine learning model that can learn and train on the go without any prepared data set. And since it's going to be real time, we have to use an edge computer. And since this is just control for something like lighting system, so we need to deploy it on a lamp or something like very, very edge thing. So that's why we had to use microcontroller, and that was the challenge here. So you know, like microcontrollers are limited resources. It's not something like Raspberry Pi, single board computer, you have RAM, you have sometimes like for Jetson computers, you would have GPUs and stuff like that. But here in microcontrollers, you have AVR microcontroller. The RAM in that Arduino Uno is 2 kilobytes. So actually, like the same model, we deployed it on Arduino, but we wanted to upgrade it on ESP32, and this work will be focusing more on ESP32. You know, also like even ESP32 doesn't have that much RAM. The RAM in ESP32 is just 0.5 mega. It's just 5 kilobytes. So this is the challenge here. How can we train or deploy a reinforcement learning model on very limited resources microcontroller? So before digging into that approach, actually we are using ESP32 along with very simple sensor, which is LDR, light dependent resistor, along with MOSFET driver just to control the lighting system. We have deployed that in multiple lighting systems, and we will see what's the performance of that and how can we deploy that reinforcement learning model. So simply in order to mimic the greenhouse, we have used that setup, just a regular LED and the microcontroller, and then the driver inside that 3D printed head, and then the sensor with the battery. So it's very simple setup. The main purpose is just to see if we can deploy the machine learning or the reinforcement learning model in that setup. So there's something called Markov decision process, which is based on something for weight updated process. Like this is the difference between the reinforcement learning and the regular rule-based or even like the regular supervised machine learning models. In supervised machine learning models, the most important thing is the weight update function. So in order to update that new value or the weights in the supervised model, you have to have the labeled data set, because such function uses labeled data set and the labels in order to assess like what's the error between the current prediction and the labeled data set. So if we find another function that can easily learn and adapt the weights without a labeled data set, that would be reinforcement learning model. So there are many different ways to do that. There's a way very model free. You don't have to have any labeled data set or any identify the model or anything. It's just greedy based on epsilon, and it's trying to trade-off between exploration and exploitation between the data that is running on the go in real time. So that process called Q-learning process. So it's a very simple process. Let's imagine that we have a table or like tabular data. We have the states, which is the reading from the lighting sensor, and we have the actions that the model or the microcontroller has to take along with the states. So if you have a specific lighting reading now, the model has to take the appropriate decision to adapt or control the light based on that state or the reading from the sensor. In order to do that, we have utilized Q-learning. Inside that table, there is weights or something like weights in regular machine learning model, and that value could be updated using a Bellman equation, which is the Markov-based process. This Bellman equation takes the state and the action, and we have the learning rate, and we are trying to maximize the likelihood of taking that decision with the best option until we reach to the desired lighting level. If the model was able to do that along with the Q table, the model will be rewarding awards. If the model couldn't do that, it will be punished, or there will be like a penalty applied on that model. So simply, this is very similar way as we learn from scratch. When we learn how to walk, we are trying multiple ways. We are trying to walk a little bit, then we fell down and so on. The same way, the model is trying to achieve as much as rewards as he can until the model reaches to the desired lighting level. So I've tested the model on 13 different targets and elimination levels, and also we have tried 10 different episodes, and the episode here is how much the model can take until it reaches to the conversions or the desired level. So I've tried a lot of trials, 130 trials, 13 targets, 10 episodes. So So here are the 13 levels, and that spread of the box plot is simply how long the model was taking until it reaches to the desired level. So if that box is very compressed, that means the model was able to easily converge faster than the longer box plots. So as we can see, mostly even with the worst cases, the model was able to converge and reach to the desired lighting level after 250 milliseconds. Just in milliseconds, the model was able to reach and adapt and control the environment. The regular approaches for controlling a greenhouse or inner lighting system, you have to do a rule base. You have to have a model. You have to know what's the threshold, and you have to write your code in order to do that. In such systems, you are not doing anything. You are taking, like, the model is taking care of the lighting, the level, the control, the thresholding, and everything. So that's why, and since we are doing that in real time, and the model has to train in real time, we were interested to just analyze the how much or how long the model will be taking in order to converge or reach to the desired point. So as you can see, actually, based on that histogram of all of the trials, as we can see, like 30 trials, actually the model take just 50 milliseconds. And mostly, like the most time here at just repeated 5 times in the 130 episodes. So those all are the 130 episodes. Most of the trials with the different lighting systems and the harsh training and the dynamic variations in the system, mostly the model was able to converge in just less than 50 milliseconds. Also here, a box plot for the steps taken and the time, and this will also give you an idea how much the model has to update the weights until it converges or reach to the desired level. So here in the steps taken, the worst case was almost 10,000 or less than 12,000 steps. Steps here are not the episodes. The episode is the entire training process until the model converged to and reached to the best appropriate values inside the green the Q table. And then in the box plot here we have the time, and again most of the trials actually the model was able to converge in very short time, less than 200 milliseconds. Mostly all of the trials were in between less than 75 milliseconds. So here's also the response analysis of the model. We have here this noise, and this is the small data from the sensor. This is in the very beginning of the steady state. The model was just the sensor was reading a little bit stable lighting system, and since that was transparent, we were able to introduce difference or variations in the system. And then we applied sudden step function, just changes the light suddenly, and the model tried to, that was after the conversion actually. So this is the deployment of the machine learning model on the edge. And then the model was able to take the appropriate action that makes the reading from the very beginning very similar to the reading after that action or sudden change or the dynamic change. Most importantly also in that work, so if we control the light, we will easily be able to minimize the energy consumption in the greenhouse. It's not just for lighting system. As we can see in the future work, we can deploy that in many different systems in the greenhouse, not just the lighting system. We can do that in the heating system, humidity control, and the HVAC systems in general. The main limitation of that work is we had to deploy that in microcontroller, and since we did that, we only had the opportunity to take 64 actions and use 13 different levels. If we went more than that, we wouldn't be able to deploy that model on the ESP32 even. However, there are a couple of ESP32 versions allow up to I guess I've tried I'm still waiting for that one to arrive, but I've tried one with 5 megabyte RAM, and if we have that one ready to go, we can deploy more than 64 actions and 13 different levels in the lighting systems. But still, we can also utilize some kind of edge computers like Raspberry Pi Zero or any kind of edge computers. Raspberry Pi Zero allow you to use up to 512 megabyte RAM. So as I said in the future work, for the future work, the conclusion, we have deployed a tiny machine learning or reinforcement learning model on ESP32 that was effective for dynamic variations, and also for the future work we can use it for the humidity and HVAC system control. Again, thank you for USDA and North Dakota, and also like most importantly Dr. Solomon, because like I was actually started that work on the Dr. Zolin in his class, and then I developed some of steps in that work also on the Dr. Solomon class. So I really appreciate his help in that. Thank you so much, and thank you for USDA and the North Dakota State University.
Perfect time. Exact 15 minutes, 82 milliseconds.
Wow.
Sharp.
Tiny
Please,
MM.
questions. I have a question. What is this is the reward? How do you provide the system with the reward? What is the goal of the Q learning system?
So the goal of the Q learning system, like here we did like a miniature greenhouse system just to develop the system, develop the code or the approach, because like we had to write every single line in the code from scratch. We didn't use any libraries or packages. We have used C programming language, not Python or any open gem, or like when you use reinforcement learning. So we had to write everything from scratch. So that's why we were interested to find a framework, and after that in the future work also that would be published on GitHub or any other open source repositories, so that you can actually use the same library or the same system or framework to control whatever you want, not just in the greenhouse. Like you can just, because like it's gonna be more API, so you will have just a function, you will call that function you will choose like how much or how many actions you will be using, how many states you will be using, and then you inside under the hood, the system and the framework will be taking care of the weight update and the key table. So that's why like we were just interested in that, but we can easily do that, like deploy that in the real time. There is systems like greenhouses.
I have another question. You use LDR, but LDR is very high sensitivity to temperature, so we can get the real actual feedback of the light intensity actually. I think we can use actually ESP32 to have a Wi-Fi connection. Yeah. So why don't you, because the greenhouse system will be connected to the facility, right? So you can easily compute the whole process in another server. Like you can create a server, you can create on your lab, you can control by itself. Or are you relying on
This is
the
really good
memory?
question. Yeah, thank you for that question. This is really good question, especially in agriculture. Like we have different setups. Sometimes that greenhouse could be in very rare area. You cannot find any internet or electricity or any access. So that's why we were interested to do like that on the edge without any Wi-Fi connection. But this is very good because but in that case, that would be cloud-based model. So we are interested to do it on the edge. So this is like different approach. On the edge is like harsh, as you know, like it has limitations. I didn't say like it's the best option, but sometimes you would have to do that. Sometimes, what if we wanted to do that in NASA, like in Mars or like in the moon? Like we will not have internet or cloud. So that's why it's very important to deploy such models on the edge. We are doing research. So if you are providing that, you'll be allowing other people in different areas to do the same thing.
Yes, please.
Thank you for the presentation, very interesting work. And I have 3 questions. The first one is collecting of energy parameters. How did you collect it? 5 watts, 1 watt. How did you collect it? Is it ESP or the system, the consumption? Second question is it UNO based or ESP based? Because in the photo, I think there was UNO, but we told about ESP. And if it's ESP, how many cores would you use? 1 or 2 cores? And the third question is about digital twins. You use an experimental approach, and can we use digital twin approach so we will not make these experiments 1 million iterations, I don't know, some states? We can just apply some digital twin or simulation, so we we will not need
Yeah, I get
all
it. I
these
got it.
setup.
I got you. Yeah, thank you for the question. There are very nice questions. For the first one, like as of far as I remember, like let's go to the second one. I think like the difference, like is it on
First one is the
Arduino?
energy.
Energy.
First one is the energy. Okay, so the energy, we have used the energy meter to collect the energy. It's not like from ESP32 itself, because we wanted to do that, but we had to deploy like current sensor. And since we are in like, we are planning to deploy that actually in real greenhouse, the current sensor in real greenhouse wouldn't be able to read the, because like in greenhouses, like in real greenhouses, they use very powerful lamps and very powerful like supplemental lighting, and this like needs like very high cost current sensor. That's why we have used like regular power meter, like it's just reading the how much like power are you taking from the system. The second question, like the difference between the Arduino or like if we utilize the Arduino or ESP32. So in the very beginning, we started that system and we challenged ourselves to deploy it on AVR 80MEGA32, which is the Arduino Uno. But we faced very huge limitations like in the SRAM. In Uno, like the SRAM in Uno is just 2 kilobyte. So we were able actually to do it, but with less, as far as I remember, it was just 6 states with 10 actions. We weren't able to go beyond that. But in ESP32, we were able to do like 64 actions and more than, I think we reached to like more than 255 over 10, like 25 states. So in ESP32, we were able to scale the system more. The third question was
Uno
the
versus ESP32. Uno versus ESP32.
Digital twin and experimental
that was
setup.
the last answer.
Digital
So
twin
the
and
digital twin,
experimental
yeah.
setup without need of
Yeah, if we went to
learning
that slide,
of agent.
I really appreciate this question because like in the professional work of reinforcement learning, actually it's usually the people usually use like simulators and you know, like digital twin to do that. But the most important thing here is like so that were like a slide here talking about like the main purpose in our approach or objective is doing a model-free system. So in order to go online or like do
It's
like
not
digital
model-based,
twin,
right?
it's not model-based. Especially like in greenhouses, it's very hard to control everything. It's very hard to mimic the same thing that happened in the greenhouse. It's not easy actually, and you have to consider everything. You have to consider the cloud cover. You have to consider the lighting, that supplemental lighting from everywhere. So it's not easy, but I appreciate that we can do it actually. But the main purpose is like how to deal with the dynamic variations, the real dynamic variations with the greenhouse, like greenhouse. So I would say for the temperature, I have to do that. For the light, since the light is like just moving in the, you know, like the speed of the light, so it's very high speed. I wouldn't see any like problem when I do the light. But for the temperature, it's very hard. We have started that actually. Like our third co-author actually, he did this also on the Dr. Solomon manual. He has tried the lights, but still the heat, but the heating system takes too much time in order to do that. So we went to some kind of simulators or other stuff. Like this will be the extended work of that version of the paper.
What about transfer learning? And so you will create some model and how I can use in another system.
That's
like,
really nice. Yeah.
Like the scaling, let's say I have a very big scale system and I want to use, and let's say transfer learning, different environment conditions. So
we thought about that, especially we trained, like we started the code from scratch. So we had to write the framework and the API from scratch. So we don't have any package like Python packages or anything. So we thought about that and we were able to transfer the learning. We were like, it's very easy. The main idea here is to train a Q table. So as long as you have that Q table, you can easily use the same function in your next code and use the final Q values that you have achieved from the first one, and then deploy that as a transfer learning for the next system. However, we are also, as I said here, like we are also planning to publish that on GitHub so that you can use that same API to start your system from scratch, or even use the pre-trained weights for the lighting systems or any other systems. If it's not taking too much time, I would prefer to start based on your current setup. But if it's taking time, it's very important to use the transfer learning. But it's very easy. It's not, since it's just a Q table. However, also like it's very hard to do like deep Q learning in microcontroller. So if you are talking about the weights from the deep Q learning, we are still researching that. If we can do like and this is like future work for everybody here. Like we can also search how to do deep Q learning in edge computers or like special like microcontrollers. This is very interesting topic.
What about AI agents? We're using transformers, LLMs instead of.
Yeah, so don't forget that the main purpose here is like to deploy such systems in microcontrollers. I don't think we can just deploy one transformer of microcontroller. It's very hard to use like attention mechanism in like very limited resources microcontroller. But of course, like attention mechanisms and transformers could be used for like deep Q learning. This is
Okay,
like
Mohammed, I was too kind to give you too much floor. Now,
Thank you
we
so
are
much.
across the timeline. Thank you so much. Please. Next speaker.
Certificate.
Oh, certificate?
Yeah.
Okay, this time I will hand over. Next time, please watch out the timing, okay? Mohammed, awesome job. Okay, thank you. I'm just kidding you. The next speaker is honey concentration detection in honeycombs using image analysis and ultra-wideband radar sensor system. Presenter Mohammed Aftabi Talami from NECU.
What was the number of that? 112.
Yeah, 112.
Yeah.
Mohammed, I will keep track of timing, okay?
Hello everyone, hope you are not hungry yet. Good afternoon. Today I would like to present my paper. My name is Mohammed Aftabi Talami, and the subject of my study is honey concentration determination of from becomes using image processing and the UWB radar sensor. So in the start, I should appreciate Dr. Earl and Brady that's made the start easy for me because they talked about the pollination of the honeybees and also the effects of the honeybees in the world. So honeybees plays an important role in global agriculture and biodiversity through pollinations. Through the studies, the estimated annual cost of the pollination that's required for crops are like inside the US are like $20 billion, and honeybees are doing this operation for us, and this is one of the reasons that honeybees are important for us. So for monitoring the honeybees, we can monitor the level of the honeybee inside the honeycombs and also breedings. Honey productivity can be representations of foraging success and also the honey development and also the health of the honeybee colonies. There are different ways for monitoring and determining the honey level inside the honeycombs. So the different honey estimation methods can be categorized in 3 different methods that are manual inspection, image-based, and sensor-based. So in application, manual inspection currently are applicable inside the honey farms, which farmer they go and manually check the level of the honey inside the honeycombs. But in the research, image-based and sensor-based honey detection will be done inside the research, and they are not, they didn't go to further steps and developing inside the real world. So because of that, because for currently for detecting the honey inside the honeycombs, we need labors. There is a need, and if we are short of labors, we need to use the parallel methods to reduce the cost of the labors and use them. So in the research, most of the research are focused on sensor-based honey detections. And which they are categorized in different researches, right? Using infrared imaging or radar vibration, semiconductor gas sensor, ultrasound techniques, microwave sensors, AI enhanced gas sensors, and sensor based. And in our research, our motivation was presenting two different methods using image based and sensor based, which for image based we introduce a new simple method for determining the honey level inside the honeycomb, and also using UWB radar sensor, ultra wideband, or UWB radar sensor inside the honeycomb for determining the honey level in them. So for the methodology, first I would like to talk about the estimating honey percentage inside the honeycomb using images. So we had the sample of 7 different honeycombs, and from them we could generate the red channel, green channel, blue channel, whole saturation and value, and LSR, ASR, and blue star pictures from the honeycombs. And as you can see separately, it's hard to recognize the empty cells and full cells from the pictures alone. So the idea was how we can use these photos and combine them together to make the honey cells detectable from the empty cells. So finally we came with this equation, which is we named it emphasized honey field images, or EHFI images, which is a formula based on the green channel, blue channel, saturation, and value and light. And also these dots, they are representation of elements-wise modifications. So by having this, by generating EHFI image and inserted inside the MATLAB, also we generated a GUI or GUI in MATLAB, which by changing the different parameters through the users on the parameters like the radius of the circles, the smoothing parameter, the threshold of the brightness parameter, we can detect the empty cells inside the honeycomb, which in the next slide I explain for you how the procedure will work. So the first step is selection of the honeycomb's corners, and from that we apply the equation of EHFI, and we generate the emphasized honey field image. And after that, by applying a smoothing method, mostly Gaussian method, the adaptive threshold, a picture will be generated, which by defining a new parameter like threshold, we separate the black holes and white holes, which is mostly shows the honey cells with white and empty cells with black. So after that, by applying a Hoff circle detection, the circles with the parameters of a radius that it will be invisible, they will be found, and after that, by removing the overlap circles, the empty cells will be found, and then computing the white areas as the empty cells, and consider it as a percentage of the honey, percentage of the empty cells inside the picture. we can estimate the honey percentage. The next method is using SLMX UWB sensor reading. So the SLMX UWB sensor, which you are watching here, is a sensor that we use inside our research. So this is a kind of UWB sensor, ultra wideband sensors, which this special sensor is a chip sensor, and it transmits the frequencies by frequency of like 7 gigahertz and receive the frequencies by the frequency of like 23 gigahertz. And the work principle is by changing the material or structure, the received frequency will change, and it can detect the different materials in different distances. So these sensors currently and newly they are using in different range of the researches like environmental monitoring or rescue operations. As a simple example, just assume that this is the sensor and we have two objects, like brown object and purple object. The brown object is in 25 centimeter and the purple object is in 40 centimeter. So here is a curve that the SLMX sensor will give us. And this is the reading of the SLMX sensor, which in the start for this object, it will give us a peak, and the other one for the second object, it will give us another peak. And the amplitude of these peaks, it depends on the distance and also the material of the objects. So how we use this UWB sensor for detecting the honey inside the honeycomb? So the main idea was by increasing the amount of money inside the honey hive, then a UWB sensor will read more peak inside the readings. So what was the problem? We needed to put the honeycombs inside the environment that there is no other object that can make this kind of curve, and we only have this kind of curve in our work. Because of that, we designed a new structure, and the structure is a wooden platform because the honeycomb itself is made by wood. So we made the structure with wood. So from two readings, it doesn't make any error. And also honeycomb just hang from there. And SLMX sensor, which is on top of the tripod. And here is the dimensions for the test setup, and also the test setup for position inside the isolated room, which is covered with the isolator cones with the special properties which absorb the noises and noise frequencies. And also the UWB sensor itself, it's stayed in a position which is centered inside the honeycomb and pointed to the center of the honeycomb. So how was the results? And well, let's see, from the 7 different samples that we had, we sorted them through their weights and mass. And so in the first set, we can see that the mass of the first honeycomb was 0.6 kilograms, and the last one was 2.7. But 0.61 was empty honeycomb. So because of that, we consider that 0.6 is the weight of the honeycomb frame, and we reduced this value from all of them, and again we started to calculate the percentage of honey inside the honeycombs. The other readings are image output and also UWB sensors reading. So for image output, this is important because for honeycomb we have 2 sides, and for each side we will receive the different readings. Because of that, by reading the percentage of the honey for each side and making an average value for them and calibrate them again, the new values of the image processing are done, and the same operation for the UWB sensors reading for different honeycombs. Here is the graph that's the results of the honey image processing estimation of the weight gave us. So for different samples, it gave us a good curve and good accuracy with the R squared value of 0.96. And here are the raw data that we collected from the UWB sensors, and by selecting peak of each of these curves, we made this plot, and you can see that for the values more than 50%, it's somehow accurate and it is working somehow correct. But for the values less than 50%, the values maybe they are not that much satisfying. Finally, here is the correlation matrix that you can see that R value for estimate the image processing is like 98% or 0.98, and for SLMX for UWB sensor is like 82% or 0.83. And as a conclusion, I can mention that we propose a simple way for making the for image processing way for detecting the honeycomb amount inside the honeycomb. Because that was somehow semi-automated way, because we need for that one a user that change the parameters and make the readings, and for the UWB sensor we could detect the honeys, and it was somehow accurate for the honey level more than 50%. And for the future works, because UWB sensors, they are so sensitive for objects in the environments, we plan to reduce the wires and make it Wi-Fi. Also, we will apply the machine learnings and data analysis for both methods of image analysis and UWB sensor readings, and we will do further studies on the live honeycombs and in a live condition. Finally, the funding of this project was from USDA Agriculture and Research Service Project, and there is an acknowledgement to USDA for supporting and providing the beehive and beecomes. Here is a list of references, and thanks for your attention.
37 seconds, 80 seconds, 7 milliseconds overtime. 2 quick questions, because we already reached the timeline. But if you have more questions, we can discuss later on. These guys will be around. Please. Any? Everybody looks like very hungry, huh? Muhammad, so this from these 2 methods, image and ultra wideband, which one is from practical perspective for beekeepers like Brady's grandpa or Jules' parents, beekeepers I mean, which one is more practical?
So using the physical sensors, UWB sensor will be more practical for beekeepers, because also it's cheaper and it will be applicable to be inside the honey hives. But for image processing, because inside the honey hives, maybe putting camera lens and make some, it doesn't make sense. So again, you need another labor to bring out the honey hives and see the, make a picture of the honeycombs and detect the percentage of the honey. So maybe it's not that much logical. So using the physical sensors that can be installable inside the honey hive will be more logical.
Thank you. Definitely they will criticize us if you do so, right? Any other questions? No? Please join me one more time. So we have two more speakers. I need to ask the permission from chair. Are we gonna go on or we will do after lunch?
What time is it now?
Lunchtime?
Lunch is 1:15, I think. Lunch will be in 1:15.
1:15. Still, we have two more presenters. because
Yeah, we can.
We can go ahead.
Complete, yeah.
Yeah. If you give me the green light, then the next presenter is 120. Yeah. Sensor for sugar beet decomposition dynamics monitoring. Rafat Safayat from NDSU, he will present. So, Rafat, floor is yours. I'm gonna fix the time, okay?
So, hello everybody, my name is Rafat. So I'm an associate in Ag and Biosystem Engineering at CDH2. So you can see that sugar beet. What is sugar beet? I didn't know also when I came to US, but later I used to know that the sugar beets are used for harvesting sugar. But back in my country, we use sugar beets a lot. So it was really interesting for me, and this drives me more into the research. And so I'm going to present sensors that I'm using right now for sugar beets. So in the picture, if you can find me, then that's a thumbs up. So I'm in top of a sugar beet, just assessing like how the sugar beets are getting in this winter season. So a bit introduction about the sugar beet and its contribution. Around 58% of total US sugar beet production happens in the Minnesota and North Dakota area where we stay. It's definitely NDSU. And what happened is that 70% of the sugar loss happens due to this storage condition. And there might be a question like, yeah, it's really cold out there, but why the sugar beets are getting rotten over time? And 10% sugar loss happens for decay. That's one answer to that question. And another 20% is the fermentation. So about the loss, we all about things about money, like why you're studying this thing if there is nothing happening to that certain. So you can see the money, it's really high, $100 million. So that's a big loss for that area. So what happened is that there are different methods that people are using right up now and which are really labor intensive. Something like grid sampling, where they sample grids for 30 days and see what's happening, but that's not that much effective because they're not getting inside the roots or seeing what's the dynamic happening inside the sugar beets. Visual inspection, you can just visualize and see that, whoa, this bed is damaged and that one is good. There's a bad smell over here. And ventilation critical. I will talk about this one more. So what happens is that if you don't ventilate these huge sugar beet piles, you can see 1.6% loss of sugar will be there, which the sugar company will not be happy at all. So on my next slide, you can see a pile over there, and it's totally outside the pile. There's snow. That means we live in an area where we have lots of snow, and those are the ventilation cavity that they use for ventilating the sugar beets inside the piles. So we are doing ventilation, but still the decomposition of sugar beets is very prominent. And during the winter season also we see this kind of problem happening all the time. So we need a sensor system which can detect the spoilage and also which should be robust enough to work in this harsh environment where there is very bad smells and water, humidity, and those kind of things over there. And believe me, if I went to the top of the sugar beet piles, and if you guys go there, you will not eat any sugar. So something like that. So our main objective is to reduce the sugar beet spoilage by non-invasive detecting internal change and rotting dynamics. And I want to thank my co-author too, Mohammed, to help me understanding these things a lot. So yeah, we use two kinds of sensors for off now. I will get off with other sensors that I will be telling in my future work step. So the ultra-wideband radar and the SHT45 temperature and humidity sensor. So the ultra-wideband radar is used pulse UWB radar, and Mohammed has talked a lot about it in our previous presentation. So I will not go deep into that. And why SHT45? We talk about harsh environment, which is very low temperatures during the winter season of when the storage are being done. And so that's why we are looking deep into this SHG45 sensors. Next, this is the experimental setup, and obviously the operator is me. So we have a drum over here, and inside the drum, on the top of the drum, we set the SLM X4 sensors, and the sugar beets were kept inside the drum. And we made it soundproof because the SLM sensors are really sensitive, and there was some connection cable. And what we did is that we use a laptop as a DAQ to collect the system, collect the data. So we collected data for around 10 days. Every day, I used to go there and collect data for a certain amount of time to see how the dynamics is changing step by step. So in my next slide, this is all the methodology that I used. The pictorial representation that was in my previous slide, you can see the experimental setup, how we set it up. So that's the drum, the soundproof cones, and one thing you can see over there is that, this SHG45 sensor, what we did is that when we do the experiment with the UWB sensor, we remove the SHG45 sensor, as the UWB sensor is really sensitive to other sensors, so we don't want to like interpret or like destroy the data of the UWB sensor, but the SHG45 was monitoring day by day all the time. So, and for microcontroller, we use particle argon, which is a really good microcontroller for taking the data online through ThinkSpeaks or any other system. So regarding the results, so we can see two results over here. One is with the temperature and humidity data, and another one is the UWB radar data. So our thing was that we want to see that how the dynamic of the sugar beets are changing over time on a constant temperature condition. So we did the experiment in a room condition where the temperature was 22 degrees and the relative humidity was around 58%. But when we studied the temperature and humidity data, we saw that the temperature inside the sugar beets, it went up to 30 to 32 degrees centigrade, which is really high because the outside temperature is not is around 22 degrees C, and the humidity inside that certain drum went up to 98%. So the humidity and the temperature is a really good factor that we should always monitor to see that how the dynamic is changing inside the beet piles. And you will see some data gaps over here. What's the problem with the data gaps? Because of the high humidity and the moisture, it is destroying the sensor a lot. So we are also thinking in our future step to include like how we can compact the sensors and make a waterproof session for this sensor so that it doesn't get affected by the humidity and temperature. On the second graph, you can see that when we took the data for 10 days right of now, and when you can see that from the day numbers, like day 1, day 2, day 3 to it's day 23, but we took the data of 10 days, and the height of the sugar beets, they're decreasing day by day. Like they're getting rotten and all are smashing together. And that is one thing that I get to realize, that when I was in the beet piles, I saw this kind of sugar beets and they were all smudging together. And the heat was really high too. So that proves that the UWB sensor is able to detect the changes that's happening in the sugar beets. And you can see in the data that there are some other peaks too. As the UWB sensor being sensitive, he's also sensing the drum's wall, and some like from 0 to 15, you can see the sensor has some reading, which is the drum wall. And again from 30, I think, 50 to 80, there are some peaks too, which are the surrounding like the bottom of the drum. So we excluded that one, but zoomed into the main side where the sugar beets is changing over time. So this gives us some good insight of our future works, like how we can engage more sensors into our system and see the sugar beets change in the huge area or the huge piles over time. So conclusion and our future work. So our conclusion is that the dual sensing system of SH45 and UWB sensor for detecting spoilage, we were able to detect the spoilage happening over time, and it was non-invasive real-time monitoring was also there. But the main issue that think us more was the condensation and the sensor stability. For future work, we are planning to add a carbon dioxide sensor. For now, we are sticking into SCD30, but we will be changing it to SCD41. So, and design moisture and insulated housing so that our sensors don't get disrupted, and employ it to the main field, which is like American crystal sugar, where I work with some of the sugar fields. So that's all of my presentation, and thanks BSD Agriculture Research for the funding, and for the experimental center, I want to thank Dr. Neela and Dr. Monono for giving me the facility to work in that place. And so the references, and thank you. Any questions? And this is we are from Agri-Mechatronics Lab, so if you want to know more about our lab, you can just scan the QR code. Thank you.
Thank you, Rafat. Perfect timing. Please, we have open for any questions for Rafat. Okay, yeah, please.
Yeah. What about the PCB and assembly components? Where do you print them?
Oh, PCBs? Oh yeah, we do the design on our lab, and we print it through JLC PCB.
GLC PCB. Okay.
Yeah, so something like that.
Again, one more time, practicality aspects. Which one you would recommend from practical aspects?
Yeah, from practical.
UWR or this, the setup you designed?
So I will mainly stick on to the setup of this one that we are developing right in the lab condition, because what happened is that in a huge pile, manually going there, and I already told you all that you will not be happy to go on the top of the sugar beet piles. It's not good. So if we just put one of the sensor box inside the sugar beet piles and see how the carbon dioxide, the VOCs, and those changes are happening, so I think that will be more like good to understand the rotten dynamics of the sugar beets. So yeah, obviously the PCBs and with sensors will be great.
Two more comments, just to make sure the others will catch you what you're working on. The challenges with these sensors that you're working with. Just mention it, a few things currently you're working on.
Okay, the challenges.
Two challenging issues you're facing.
Okay, we use sensors that are off the shelf, like you mentioned, something like DF robots and those kind of sensors for VSC sensing. So what happened is that on last year, we tried to use their algorithm and try to see what they're giving us, but it was a long period of time, around 120 or 30 days. At some points, the sensor got really off, like they were not just giving us good data, and they were giving us something like high and low data, those kind of data. So that think us more like how. And then I saw that there were some humidities in those sensors that's disturbing the sensors and making them damage. So these are something that that I need to also work on at our lab, because in that condition where there is lots of beets, there will be water, sugar, and humidity, everything bad that need to happen is there. So this is one challenge that I face the most in my research over time, and I'm trying to get out of those things. And regarding this PCB design, we are focusing more on the quality of data. So we have good quality of data, like if we are seeing some kind of ethanol inside it, it should be 100% ethanol, or the ethanol that it's sensing should be ethanol. So we are doing some more tests with like laboratory condition with GCMC, where they test different kind of ethanols and try to calibrate this sensor according to that like state-of-the-art machine. So our sensor gives good data and reliable data. So if we call at the American Pistol our customer, they will be really happy with our products or something like that.
One last question, anybody? Yes, please.
What about the data collection, data monitoring, like UI something? Is there anything for users, let's say American
Okay.
Crystal Sugar Beet
Okay.
operators?
So for that, another problem in these sugar beets files are internet. So in some of the places where we go, we don't have like any cellular networks or those kind of things. Our Wi-Fi, we don't even think about Wi-Fi. So we are trying to use LoRaWAN, like LoRa networks. So what we are trying to do is that, like, there are some managers like sugar beet, like they are in charge of a file,